Right, integration. Let's give this a go. So hope we're all geared up for this. We're all ready to go. This is, there's a lot to it. I'll explain what we're going to cover. But the plan is to cover integrating powers of x, trig and exponential functions, reverse chain rule, area under a curve, and first order differential equations. And then some of these very tricky methods like partial fractions, substitution, and by parts. So we're taking on a lot. I hope we've got the energy to do this because it's like very full on, and then it will be the stats. So let's give this a go. Let's get straight into it. Now, to start with, simple integrals, integration and calculus is on all the boards, and the level of depth is basically the same for all of them. It's one of the biggest topics. So the first thing to just remind ourselves of, fundamental theorem of calculus. This is very straightforward in essence. It basically is something we use a lot in year 13 in the background. It's kind of exploiting the knowledge of derivatives and integrals being the reverse of each other. So all it is basically saying is that the derivative of a function is, if you integrated it, you would get the original function. So derivatives and integrals undo each other. So basically, if I have the derivative and then I integrate that derivative, I get back to the original function. That is the fundamental theorem of calculus. So it just takes me back to the original function plus what? Plus hopefully C, potentially, if we're doing indefinite integration. There is a constant that could emerge. So we've got to look out for that. Right, let's power through. Now, really sort of basics to start with, looking at like reversing the process. If we've got each of the following. Now, if I have f of x differentiated is 1, then I should know that the integral, do you know what? I'm going to use green integral, color code it. Integral of 1 with respect to x is x plus c. So it undoes that process. Likewise, if I integrated 2x with respect to x, I would get x squared plus c. Okay, now in general, if I integrate x to the n here, I'm going to get 1 over n plus 1 of x to the n plus 1 plus c. And just a key reminder with constants, if I integrate a constant, I'm going to get, sorry, if I integrate 0, I'm going to get a constant, which is basically like why the constant always appears. That's what we're talking about. So let's look at some basics that you should hopefully all be confident with, because we've got a lot further to go with this, but just almost like a refresher of year 12. Plus, I mean, you shouldn't need long for this, but let's give this a go. And it's asking for a specific point. So I think like 40 seconds or so, we'll quickly whiz through it. Give it a try. And then we're going to go through some standard integrals that we should know and start looking at the process of recognition. Right, so you've got the derivative and you want to work back to the original function. So 2 marks should be quite quick. Integration to undo differentiation. Here we go. So if you integrate both sides with respect to x, the dy dx becomes y. So we get y is equal to the integral of 4 minus x squared. Now, if we work this out and put it together, the integral of 4 is 4x. The integral of minus x squared is a minus a third x cubed plus c. Now, the key thing to remember is you were given a value to sub in, which you must make sure you sub in and then solve. And so we're going to get 10 is equal to 4 lots of 6 minus a third lots of 6 cubed plus c. Rearrange, find c, and you get c is equal to 58. And then you've got the exact curve. Don't forget to state the final answer. Now, let's look at integration of trig and exponential functions and just some standard integrals that we can be aware of. Okay, so this really, really does mean we need to be confident at differentiation so that we can reverse the process. So sine x we know differentiates to cos x. So off the back of that, we know the integral of cos x is, of course, sine x plus c. Now, the derivative of cos is minus sine, so we have to be careful here. The integral of positive sine will therefore be minus cos. Okay? And then e to the x differentiates to e to the x because it's pretty good like that. And then that means it would integrate back to e to the x as well. And then finally, this is the one to look out for. Ln differentiates to 1 over x, meaning that we actually need to spot when we've got a fraction like this, that it's going to be a log. It's going to be ln of x. Because notice the year 12 method of x to the minus 1 to integrate doesn't work. Because if you add 1 to the power and divide by it, you can't divide by 0. So it's a whole different thing. Right, let's have a little look. So at the following. So like we did earlier, we can now fill these in. If you have your formula book handy, or you know what you're given, or you know your derivatives, you kind of know them the other way round. So if you're asked to integrate, oops, oh, not again. Sorry, guys. Here we go. If you're asked to integrate tan sec squared, it's going to be tan x. And if you're asked to integrate cosec squared, it's minus cot x. Please do take the time to look at what's in your formula book, because you get more than you think sometimes, and you can just use the derivative backwards to work out the integral. So here are some that are worth filling in. Right, guys, that does say tan x, but there's a weird bit of the screen there that if I write on it, it sort of messes up. So I'm going to just leave that as it is. Let's keep going. Now, here's a question. Here's one for us to try. I'm going to give you a minute head start, then I'm going to start powering through it behind you and see how we go. And then we're going to start properly looking at reverse chain rule. Here we go. Right, so 2 marks for these 3 terms that we need to work out, because some of them are about just spotting. Quite a few different things going on. You might want your formula book in front of you, the standard integrals, standard derivatives, also looking out for the trick, because sometimes we see a 1 over x squared and a 1 over x and think they're kind of the same. They're actually quite different. And don't forget the plus c at the end. Right, here we go. So the first bit, do it year 12 style. This one is, remember, a x to the minus 2. So here we go. So minus, drop the power, and then add 1 to the power and then divide by it. So for example, being careful with that, we're going to get minus 1 over x. Now this one, 1 over x, will just be one we should spot. So this is a kind of standard derivative we should know. It's not one of them. It's actually ln. So well done if you spotted that. That term goes to ln x. Minus 2 sec squared x, if we now focus on this bit, we should link that to tan, either from your formula book or what we saw earlier. And then we remember plus c. So putting it all together, minus 1 over x plus ln x minus 2 tan x plus c. And that's your final answer for that question. Okay. So we are now properly going to work on reverse chain rule. And this used to be called recognition. It's weird because it is basically like, or it feels like guesswork. And it kind of is a test of how good is your differentiation so that you can guess it and integrate. Okay, so reverse chain rule. Let's have a look. Now, what we've got is if we're asked, for example, f of x is sine a of x, then we've got to be really careful. If I ask you to integrate this, oh, sorry, there's another one for us to do. Let's give these a try. If I wanted to integrate sine a of x, the first thing I would do is I would say, well, I know how to integrate sine. I actually know that sine comes from minus cos, because cos differentiates to minus sine, so minus cos differentiates to sine. So I kind of half have the answer. I know it involves a minus cos a of x. So I'm going to put that in my answer as almost like a guess. And then I'm going to differentiate it and see how far off I am. So minus cos a of x differentiated by chain rule would actually be a sine a of x. Now I don't want a sine a of x, I just want sine a of x. So I'm out by a factor of 1 over a. That's the adjustment factor I would need to include. So I kind of know the function it's going to come from. I know that sine will come from minus cos. So I know that's going to be part of the answer. So what you could do, some people like doing this, is differentiating minus cos a of x and seeing how far off you are. Because if you're only off by a number, or like a letter in this case, you can adjust it. You can just times by 1 over that thing. So let's look at a similar one here. What do we reckon this is going to come from? This is a 1 over something x. Now, this looks a little bit nastier. And I would also suggest like the denominator's linear, the numerator's a constant. So the numerator's like the derivative of the denominator. The guess here is actually that this is a log. This is ln. So if I asked you to integrate this, and you notice that this is linked to this by its derivative, a linear to a constant, my guess is basically going to be ln of the bottom. Well done if you're confident with this, but I know that this is actually a really tough part of the course. For some people, spotting this is quite hard. So that's part of my answer. That's my guess so far. And then if I differentiate ln of ax plus b, I would get a over ax plus b. That's how you differentiate chain rule the logs. And you don't want a on the top. So it's out by a factor of 1 over a again. And that's your adjustment factor. Okay, so we're going to look at more examples like this. But some people learn this process in lots of different ways. And what it comes from, we're going to look at a much harder one now, or maybe just like a less obvious reverse chain. People think, oh, this just doesn't feel like a formal technique. It is testing your differentiation, if anything. So let's look at the following. If I give you this example, fx equals 2x e to the 2x, e to the x squared. You might think this is by parts, this is substitution, this is hard. How do I do this product of two things? But the product of the two things are linked by their derivative. Because if we look at this sort of operative part here, if you were to differentiate that, it would be a chain rule. And you also know that the kind of inner mechanism x squared, the derivative of x squared is 2x, which pops out. And it does pop out in this case. So actually, my guess for the integral here, if I use capital F of x as the integral, my guess is actually going to be, it's got to be to do with e to the x squared. And if I actually did differentiate e to the x squared, I'd get 2x e to the x squared. So I don't even need to adjust it. The guess is correct. It's all to do with this operative part. If you notice that the other bit is linked to that part by its derivative, you've guessed it straight away. So in a similar way, if I introduce this question here, This is very common, and these a lot of people kind of make a meal of these questions where it's sine and cos to a power, or cos and sine to a power. This again is a little chain, and this is the operative part, because I know sine is like cos is related to cos's derivative. So I'm going to think of this as the main bit that informs my guess. And I'm going to say, I know that the derivative can work out like the derivative of this. So I know that will go to n f dash of x, f of x to the n minus 1. Okay. So what I'm saying is my guess is going to be to do with the cos bit. Now, I know that when you have a cos to a power or something to a power in chain and you differentiate it, the power comes down by 1. So remember with integration, just like in year 12, power it up by 1. So power the guess up by 1. What's going to differentiate to a squared? Something cubed. So my guess is going to be cos cubed. Okay, let's see what happens. So if I want to integrate and get the integral, my guess is going to be cos cubed of x. Now, if I chain rule differentiate that, I would get 3 cos squared x times by the derivative of cos x, which is minus sine x. And so it's 3 times too big, and there's a minus. So the guess needs to be minus a third of the size. Okay, and now don't forget you can still differentiate that and then check it does actually work. So what you've had to do is you've had to like recognize the operative bit of the function. So the e to the x squared was the chain. That's going to inform our guess. Cos to a power, let's power it up by 1 and see how far off we are. Now, I totally appreciate that still like, this is probably for most people one of the hardest skills in the course because it requires you to be super confident about everything. And you've got to be like, yeah, I'm kind of keep abreast of all the different things that are going on, then guess it and then adjust it. So this takes a lot of practice. If you feel like you're disproportionately spending time practicing this sort of thing, you're not. It should take up more of your time. And it is harder. So let's do a bit of practice now. I'm going to give you a few minutes, 2 marks each. Try and look up standard integrals, try and see what they link to. Give these a go. And let's have a little look. I think, see if we can tidy these up. They're maybe not as hard as they first look. Okay, so a couple of minutes on these, and then we'll carry on. But yeah, we're doing really, really well. So I'm going to give you 2 minutes thinking time. Okay, so we'll speed on with some of these, check them through. They just look very different in style, but actually the first one really could be tidied up. So don't forget your obvious rules you can do with laws of indices and division and stuff. This one, e to the x to the 2, is actually just e to the 2x. And therefore, you can actually just do this as a subtraction of the powers. So don't forget that that's like a thing we can do. So this is just a really complicated way of asking us to integrate e to the minus x. So that's absolutely fine to work through and give that a go. Now, reverse chain rule, we have to be careful. And it's so easy for something like this to accidentally differentiate it. So just be careful. It's still integration, but we know obviously it will have something to do with e to the minus x. So e to the minus x plus c will be part of your answer. And if you were to differentiate that, e to the minus x, a minus would come down by chain rule. So to compensate, you have to times it by another minus. So that's the main place people will go wrong. Now, it's only one mark, and you might be looking at that thinking, yeah, that's actually quite easy, but it's such an easy place to lose marks with a minus sign. And also to like mistakenly differentiate it, which arguably would still get you very close to the answer here, but you've just got to look out for that minus sign. So then the other bit, the other one that we're dealing with, this one, again, people might look at this and think, is this by parts? Is this some other technique I need to know? But because if we look at, again, the operative bit, which is in red, because the inside of that function's derivative is linked to the other thing, is linked to x, because x squared differentiates to 2x, and that's only away by a number, so like it's quite close to x, you can guess this one. So if we think of this as x squared plus 1 to the half times x, and an x thing would come out if you use that to inform your guess. Okay, so what we would do is we would go, I know that something like this would differ, sorry, I'm guessing something to the half. I'm dealing with that as the operative bit. Okay, so my guess is going to be to power that up. Now, if I power that up by 1, I'd get the 3/2. And that's actually how I would just do it. I would guess x squared plus 1 to the 3/2. You could put the adjustment factor half in already as 2/3. But the key thing is knowing that it's x to the 3/2. So it's x squared plus 1 to the 3/2 is the guess. Now, where we can go from there is that's the guess plus c. And if we have 2x coming out, but we only wanted x coming out, we need to half it as well. So the half and the 2/3 to compensate, which will make 1/3 x squared plus 1 to the 3/2 plus c. Do at this stage still differentiate your answer. You can always differentiate this and check it actually works. Check it actually gets you back to this. If you're confident with chain rule, that will work. Okay. And the way you approach that might have been slightly different, but it's still effectively reverse chain. Right. What we are actually going to go on to, like, as I said, do keep questions coming in. We're going to look at applying integration. So we're going to look at like integration as the limit of a sum, areas. And for some of the courses, I know Edexcel, certainly, they added this in one of the exams and it was missing from the textbook at the time. So then the reprints got it. But it is important that we talk about this next thing really carefully because it is in there for all the boards and it is something you should know. So we're going to look at applying integration when we're doing bounded integrals like this. Now notice that all your calculators can do this numerically, but they'll generally give you a decimal. So we've got to look out for what the question actually wants with these. So all boards are testing this stuff. And see OCR, all of them have it as a limit of a sum. So AQA has it, OCR has it, and Edexcel has it. So that's what we're going to start with. Now, this idea gets glossed over quite quickly But it kind of ties in with like trapezium rule and stuff you've seen before. An area under a curve can be thought of as loads of little strips of area. Okay. And the more strips you take, the closer to the true area they'd be. So it's almost like an infinitely small strips all added up would make that area. And the more you take, so this is where it ties in with limits. So as the width of these little rectangles or trapeziums get narrower, it would actually get closer to the true integral. If you haven't seen this before, please make a note of this, because some of the examples put this question in the exam with this sigma notation before, and no one knew what to do. And all it means is literally integrate it. Okay, so if they asked you to do this for this function between 5 and 2, you just turn it into this. It's just not letting that notation throw you off. Okay, so this is where people got all in a big flap and they were like, it's not worth loads of marks, but I don't actually know what it means. Let's do the limit of the sum of the function with respect to these little small changes. All it means is integrate it between those bounds. So it's just like not letting that notation phase you is what we're getting at. So all we're doing is we're recognizing integration as a sum of little areas. So the limit of a sum of rectangles, let's say, from A to B, which are X bounds. Okay, that's all this is. And we're just adding these areas up. And that's as we shrink the width, as these get smaller and smaller, it will fill up that area more perfectly. And ultimately, it will represent that integral. Okay, so that is a really important point to make, because that notation has thrown people off in the past. Right, let's keep pushing on. So this one here, so looking at this question, therefore the integration of a function gives the area between the curve and the x-axis between those limits. So this is another thing to remember. When you're doing an area, you don't put plus c, because first of all, it's a subtraction, so the c's would cancel anyway, but also that's a different use of integration. It's for a different mechanism. So if this is between B and A, and remember we want to denote this properly, this would be f of B subbed in minus f of A subbed in. So even if you had the constants in there, they would cancel anyway. So the better convention is just not to write the plus c for this kind of question. And that will evaluate the area underneath. Now, also, because people do get a little bit confused with this when we've got two curves going on, when you've got two different functions, what's really good about this is you only actually have to integrate once if you do the bigger one minus the smaller one. Because what happens is if, for example, this is between 4 and 2, if we imagine, how can I color code this? If I say area 2 is this one, and I say that's the top function g of x integrated. So area 2 is the integral between 4 and 2 of gx with respect to x. And area 1 is the smaller one under this curve, which is the integral between 4 and 2 of the f function. Then the area between them is area 2 minus area 1. Okay, so basically find the area under each curve and subtract them. Now, what we can actually do, we could do that as two separate integrals. But what you can actually do is just do the integral of the above one minus, so work out that function minus that function and then just integrate it once. I wonder if people have seen that before. This is really quite helpful. Rather than doing two integrations, you can take them away from each other and just do one combined integral, if that's the case that we have, if it stays above it for the whole time. So it's a really, really good one to do. And we're going to push on to some slightly harder questions of this now. What I'd like you to try is this one here. So if you've got the area, you can do them. If it's easier as two separate integrals, by all means do that, especially if you don't know how it looks, and then just take them away. But it says calculate the area between two curves. F of x is x squared plus 2, and g of x is 1 over x plus 2 all squared. Between 0 and 2, you should show all your work in and leave your answer as a single fraction. Okay. So let's have a little look. 5 marks. So there's quite a lot going on here. 5 key steps, probably 2 for each integral and 1 mark for putting it all together. Can't just plug it into a calculator. There's your graph. Are you given a picture of the graph? I think you are. So I'm going to give you 2 minutes to try it. And then I'll maybe just try and start integrating it. And then I'll catch up with you and see how we're getting on. Really well done, guys. You're doing great with the perseverance here. It's just like full on calculus this afternoon so far. Really well done. Really appreciate it. 2 minutes and I'll check back in with you guys. Well done. Okay, so another minute or so, just maybe 40 seconds, and we'll start going through it together. Well done if you're almost there or you're kind of getting somewhere with that. That's brilliant. Next thing we'll focus on is first order differential equations. So we're hitting all the big topics here, but as I said, doing really, really well. So let's keep going. Okay, so we'll start going through this together. There's the graph that hopefully you've been presented with. And so the area under the first curve, x squared plus 2, hopefully not too bad. The bounded integral between 2 and 0, which many of you, your calculators will do. And it was almost like a year 12 style one. Just be careful, like leaving it exact stuff. So that's what we've got. And then we need to do the integral of g of x. So, sorry, finding the area under the first one, actually subbing 2 and 0 in, and we'll get the following 20 over 3. Check you got that, because that would definitely be worth 1 mark and a mark for working as well. So as we said, it's probably 2 marks for each area and then a final mark for putting it all together. or doing a subtraction and showing that. And you may even get that final mark if one of them's wrong, but you showed that step. So the second curve, the integral, this isn't an ln one, this isn't ln because it's squared, it's a reverse chain. So this would become a -1 over x plus 2 because it's like x plus 2 to the -2. So that's the one to be careful with. And then again, we're subbing in the bounds of 2 and 0. So for this one, if we sub 2 and 0 in, we get a quarter. We're all happy with that? So just check. Now, I think that was the harder integral. So just going back, because I'm worried that was a bit quick. This one we've got to be really careful with. It's not ln. This is actually hard. The first one was very like a year 12 style, and hopefully we got those 2 marks. This is like x plus 2 to the -2. So the guess is power it up by 1, so x plus 2 to the -1. And if you differentiate that, a -1 would come down, and it would be minus x plus 2 to the -2. So it's off by a factor of -1. So the actual integral to this is this thing here. And I'm aware that this might be the harder bit. So please check that if that's affected you there. Because I know we can sub bounds in and I know we can tidy it up, but this is probably the pinch point of the question. Okay, so then you sub 2 and you sub 0 in to that. And so at that stage, you would have -1 over 2 plus 2 minus, be careful with all these minus signs as well. It's only up to a quarter. So we've got the 2 separate areas under each of the curves. And even looking at your graph, guys, remember that that other graph that's near the bottom, it's got a really tiny area under it. So it probably looks right that that's a really small fraction. So then when you take them away from each other to get the gray area in between, we're left with this as our answer. So feel free to make a note, even if you need to rework it or check. But what we'll do is we'll push on if you're happy with that. Okay, brilliant. So what we're going to do now is we're going to push on to first order differential equations. These are brilliant because this is such a big topic, quite useful in the real world, but it's quite annoying that it comes so late in the course that we don't have time to take it in all the time. It's like we're just suddenly in it and we're practicing it, but they're really important and really useful. And we need to invest time in practicing this. So we're going to begin by the separating the variables process. So just as a quick context, first order differential equations are when it involves a derivative like dy dx and potentially a function of x and potentially a function of y. And we want to get the x's with the dx's and the y's with the dy's. So this is all about rearranging. Okay, so this is what the aim is to do, this separating variables. So if I give you an example here, if I say, for example, dy dx, and I'm going to try and color code it again, equals 2x squared y. We want to get the y's and dy's on one side and the x's and dx's up. And none of this is by plussing or minusing. It's all by timesing and dividing. So where we would go with this is we would go 1 over y. I'd divide y to that side. And then I'd times up by the dx. This process is called separating the variables. I'm going to stick to the one pen here now because it's probably take ages. So this is where we would get to. Sorry, I've times up by dx. And then what's brilliant at this stage is we've got the correct derivative operator part with the correct term. So if I drop an integral sign on both sides, I'm integrating the left with respect to y, so I just do it in the normal way. And I'm integrating the right with respect to x, so I'm doing it in the normal way. So this isn't like earlier when we were doing always with respect to x. It's you just integrate both sides in the variable that they're in. That's why this is important. So 1 over y with respect to y, what's 1 over something integrate to? This would be ln y. And on this side, 2x squared, you're confident in integrating that. That'd be 2/3 x cubed. And then we're going to put plus c. Now, guys, just a little reminder, even if you've done this before, we don't need to put plus c on both sides. In fact, we don't want to do that. And the reason is, technically, both integrations would produce a constant. But if they're both constants, you can just move them to one side as one constant. Because if it's like +2 and +5, that would just be like +3 on the one side. So you don't, rather than having loads of constants, just write the constant in one place. So it's not like you've done it in a sloppy way and you haven't integrated properly. You have, but you've acknowledged that we can just put the integrals constant all together on one side. So let's keep going. And if we were to carry on with this example, so we might want to actually rearrange it. We don't really want the answer in ln y. So we currently had it as ln y equals 2/3 x cubed. And the biggest thing with these types of questions is it's just the format that they're given is a lot of manipulation at the end and at different stages. So here we don't want ln y, we want it in a sort of Cartesian form. So how do we undo ln y? We raise both sides to the power of e. And I can't stress enough, this is just like any equation you would do. You have to do the same to both sides. Now, there's another sneaky convention that's going to come out of this. I wonder who recognizes this here. This is like e to the something plus c. This was a step I remember in my A levels being like, why have they just made up this new step? And I didn't know where it came from. The e to the c bit is the unknown. So we need to think of this as e to the c times e to the 2x cubed over 3. And then conventionally, they use the letter a for that. So I'm just going to reiterate what's happened here. But rather than having the unknown constant in the power, you can call it whatever you want. I've called it a because most mark schemes call it a. But when you sort of take both sides to the power of e and the constant is now slipped into a power, remember from power rules that something to a power plus something is like a product of the two things. And then e to the c is actually just a number as well, which would come out as a multiplier. So it's much nicer having it there when we want to sub stuff in to then find it. And that's the step I think people struggle with. It's not nice having the constant mashed into the power of something awkward and clunky. It's much better writing it like this because we can even understand that better as a graph transformation. So now, if we're given a particular value to sub in, for example, a pair of coordinates, I'm going to give us the pair of coordinates for this, 0, 4. So if I give you 0, 4 to sub in as x and y, what we've got here is this is called the general solution. So in year 12, this is like when you say, I've taken the derivative and I've got an answer of y equals 2x plus c. Then I give you a coordinate and you find the particular solution and you work out what the plus c is. That's exactly what this is, but it's a much harder type of equation. It's an exponential. And instead of finding the plus c, we're finding the a, which is the other constant. So the constant of integration has got absorbed into the function. And we still want to find what it is. So let's do that. So what we've got is we can think 4 equals a e to the 2/3 0 cubed. I'm subbing in x and y just like I would always do. Now, e to the 0 is 1. So 4 equals a. So basically what that tells me, my particular solution, my final answer, is that the answer is y equals 4e to the 2x cubed plus 3. So unlike the classic polynomials we do, where the plus c is what we find out tagged on the end, the plus c has got absorbed into the function in a way, but we've still stuck in the x and y values to find it. So this is a lot to this, but it's a really good question to practice first order differential equations. So I'm going to give you one to try now here. of this topic that just looks horrible, but let's talk it through together. So 5 marker broken into 2 parts, 3 and 2 marks. We've got lots of information, so we'll sift through and work out what we need, what kind of answers we would expect. So we're looking, there's lots of letters, it's horrible to look at. Initial radius, we need to think what that means, and we need to go through it. So certain stars rapidly expand at the end of their life. One star expands in such a way that its surface area, S, increases at a rate given by this. So the surface area, that will probably be d capital S dt, where k is a proportionality constant and t is a time in seconds. And we're going to think of the star as a sphere. Find the general solution to part I in this form, stating the constants alpha and beta. Given that k is this, find the initial radius is this. Use it to work out the surface of the star after 1 second to 3 significant figures. Right, so this is a little bit like mind-blowing question. I'll give you 2 minutes again, head start. But remember, link it to the skill we've just done. Can you come up with a derivative? And can you start to separate variables and integrate? Okay, so a couple of minutes to have a little think, and then I'll follow up with some answers and how to go through it. Really, really well done, though. So this is where it's getting quite intense. Yeah, a couple of minutes, 1.5 to 2 minutes start ahead of me, and then we'll break it down. And I'm conscious I don't want to rush you with this, so we'll take as long as we need to go through it. So yeah, keep going, and it is a big one, but don't panic. Okay, let's have a little look through this one then. So we'll see how we go, and then we're going to look on to integration methods by parts, substitution, and some of the other techniques. So here we go. This question doesn't look too nice, but we'll go through it together. So first of all, we're going to derive the rate of change for S, ds dt. Now we're told in the question that the surface area S increases at a rate given by 2kts. This is very similar to the topic we did earlier in differentiation with rates of change, like comparing the derivatives, bit of shape, and they can link these topics together, as the examiners had said they like to do. So we know from that all that kind of complicated wording that ds dt can be set equal to 2kts. So like we said earlier, because it said the rate of change of the surface area, that's ds with respect to time. So we can set that up. Okay, brilliant. And notice that that is with respect to time. So this is straight into separating the variables. This is straight into get all the bits with t on one side and all the ds's and the s's on the other side. Remember, none of this is plussing and minusing. It's all to do with timesing and dividing the right bits round. Okay, so separate the variables is what this step is called. And if we do that, if we separate the variables here, then what we're going to have is I would divide by the s, keep that one as simple as possible because it has to be on the same side as the ds, times up by the dt, and then we've got 1 over s ds, 2kt dt. So we're ready to integrate. Okay, and then we're obviously aiming for the answer they asked us to show. So the 1 over s, very like the question earlier, that's going to become ln of s. And on the other side, remember the variable we're actually integrating with respect to is t. K is not a variable, K is a constant. So whilst it looks quite waffly and like there's loads going on, t is the thing we're focusing on. That's the bit we're integrating. So from here, integral of 1 over s ds is equal to the integral of 2kt dt. This is what we're integrating. So we do each integral. So 1 over s will become ln s. And then the other side, we just do like year 12 style. And we put the plus c on one side. So this is where we're at. We will get ln s is equal to kt squared plus c. Because if you integrate 2kt, power it up, divide by the new power, you're going to get kt squared. Okay, and you put the plus c. Now remember, we don't want ln s, we want to make s the subject. So we've got a little bit more work to do because we want to get it in this form. So ln s is equal to kt squared plus c. So I'm going to raise both sides to the power of e, which will kind of unlog it and get us s. And then we've got e to the kt squared plus c on that side. Now remember, we said that e to the c can be just called a, capital A. So we know that e to the c is basically a. And we've got kt squared. And if we compare it to the thing they asked us to show, well, k is alpha, t is there, and beta must be 2. It's literally a complete match to that. We have got it in that form. So we've sorted it. Okay, so well done if you kind of got somewhere, or you, even if you got it to this stage, you've understood the separating the variables. There was a lot of context. This is a big maths question. You had derivatives, rates of change, separate the variables, integrate both sides, tidy it up in a really specific way. So very, very well done if you got that. And even if you didn't have enough time, but you followed that, that's really reassuring because it's a common style of question. Cool. Now, to actually determine the value of A for part B, they have scaffolded this question a bit. They told us the initial surface area. So they have to give you something to sub in. So they're telling you at time 0, this is almost like a bit mechanicsy. They're telling you at time 0, the surface area, whatever it was some massive number. And that must be what A is equal to. So the initial radius was a little bit nastier because they said the initial radius, and they've said it's a sphere. So it's 4 pi r squared. they told us the radius. So we know that at time 0, the area will literally just be 4 pi r squared, where we sub in r as the initial radius. So I'm just going to give everyone a minute to hopefully check we're good with that. What we were getting at early on is that a e to the 0, this bit, is that when you sub in t as 0, the e to the 0 goes to 1. So normally what we're saying is this a just becomes the initial condition, which is the initial surface area. But they didn't give us the initial surface area. They gave us the initial radius. That's what we have to sub in. And then they've said the surface area at time 1. So we're putting in t as 1. And we were also told k in the question as 2.65. And we were also given R0. So now it's just literally subbing everything in that they gave us. So what we get is we put all of that together and then find the surface area. So it's not a very nice number. Look out for your units as well, and that's what we get. Okay, brilliant. Right, this does take a bit of stamina, but we're doing so well. The next thing is going to be the specific integration techniques. So by parts, substitution, and so on. We're going to push through this for probably about half an hour, and then take a break, and then it will be the final session, which will be on statistics. So hypothesis testing and stuff. So integration methods, let's give this a go. And we're going to start, because again, this is crucial for everyone to practice. We're going to start with the partial fractions ones. So this is like why we do partial fractions. And when we first do it, we're like, oh, it feels like maths for the sake of it. It actually becomes useful for these kind of logarithmic questions. Now here, remember that this will just be like b ln x plus b. Okay. If we can get it in this format, they're quite easy integrals. You might still not be that comfortable with log integrals, but it's much better having it in that format than trying to have it like this. Okay, so here we go. So what we're going to do is the first step is to convert the algebraic fraction into the partial fraction form. So if we have something like this, we factorize the denominator. Often it's factorized for us, and then we equate it in the partial fraction form. So we need to basically work out a and b, because this is a lot nicer to integrate than this. Okay, so let's keep going. Let's do an example and then a practice one. So for example, here, we look at the denominator factors. You've probably got all your different ways you do partial fractions, where you go, okay, I'm going to sub in specific values, or I'm going to compare coefficients, however you want to do it. So I would probably sub in minus b and like minus a and use that to work it out. It actually looks really horrible in general terms, but if you're confident with partial fractions, I'm keen to push on where we actually do this with numbers. So let me push on to a clearer example here. This is quite nice. Just look out for the repeated root. So hopefully we all know what that means. If it's x plus 2 squared, you have to consider an x plus 2, an x plus 2 squared, and an x minus 3. So because the repeated factor, we're going to set it up like this. So just a little reminder, because they might not guide you to do that. This is what we do with a repeated factor. So hopefully we're good with that. And then what we're going to do when the highest power of the denominator is more, the other thing we have to look out for this is improper. For this one, you would do like polynomial division, or there are some little tricks you can do as well. But for this algebraic long division, you can't have the power in the top greater than or equal to the denominator. It's like top heavy, it's improper. So the aim would be like rewrite it like this. because this is the remainder from polynomial division. So what we're saying is, because if we look at the powers, the highest power, hopefully you all know what I'm talking about with this being improper. The highest power on the top is 3. Highest power on the bottom is 2. This is definitely improper. So you're going to do polynomial division. And what you find is this is the quotient part and this is the remainder. So we put that over the original thing, the divisor. And then this is now doable. You might still need to sort that out with partial fractions, but this is now doable using integration and partial fractions to split the fraction up, okay, because it wasn't nice to start with. What we'll do, we'll take it back a step and do a slightly, hopefully nicer one, and I'll let you try it. Oops. So here, so give this a go. I'm going to be quiet. I'm going to give you again, 1.5 minute head start, then we'll work through it. And then after this, we'll push on and we'll have a little look at substitution. So let's give this a go. Really, really well done. Right, okay. Let's start to go through this together. So 4 steps is actually a fair amount of work because of the partial fractions aspect. So it's like deep breath. I know this is going to take a bit of time, but I know what I'm expected to do. So this isn't one you could just guess. It isn't a nice one. It needs to be tidied up before we can integrate it with any other techniques. Okay, and remember plus C at the end. I can't keep mentioning that enough. So first thing, the bottom bit can be factorized. And actually, there's a common factor of X. So this is like those kind of maybe like softer skills or the easier GCSE skills, but we can still mess them up. So factorizing it, take X out, then you're left with dots. You're left with a difference of 2 squares. So it's not a repeated factor. It's something that can be further factorized. X plus 2, X minus 2. And we can see the level of confidence we need to be able to really factorize that into a triple bracket, but it's totally doable. And now that is going to inform us for our partial fractions. So let's now sort this partial fractions bit out, push through that, and we'll get on to some substitution. So here we go. This is what we have. And we want, this is fine. We don't need to do any long division. We actually just need to use partial fractions. So let's suggest A over X plus B over X plus 2 plus C over X minus 2. And then we need to be really careful actually finding A, B, and C. So you could times up by the factors it's missing. So A will be times by X plus 2, X minus 2. B will be times by X and X minus 2. C will be times by X and X plus 2. Now I would probably sub in 0, 2, and minus 2 to help me find A, B, and C. So well done if you did that. Hopefully that's clear up to that stage. Well, let's check we're good with that. So subbing in 0 to -2. I think the first thing we get is A as -1/4. And then if we do the same for, now we know that, sub the other one in. C is an 1/8. And B is an 1/8 as well. Okay. So what we do is this sometimes throws people when A, B, and C are fractions, but that's fine because the fraction becomes part of the coefficient. Like if it's part of the numerator, 1/4 over something, the 4 can get absorbed into the denominator. So they were the values of A, B, and C. So just going back a stage, just to check we're happy. This is where we got to. Let's just check we're good with that. You put in 2 minus 2 and 0. You got A as -1/4. C is an 1/8. B is an 1/8. And that's where we're at. So now just looking at this, if we're to integrate it, first one just becomes -1/4 ln x. Second one becomes an 1/8 ln x plus 2. And the third one becomes an 1/8 ln x minus 2 plus c. And we do need to remember the plus c. Right. Now, I know that was quite full on, that was quite tricky, and we are going at quite a pace. What we'll do, we'll keep marching on with these techniques. We're going to look at substitution next. And then, yeah, we'll carry this on, and then we'll take a break before doing statistics. If you have any questions, keep them coming in, and do try and keep up with this. As I said, with the mini mock stuff, you're going to be emailed the solutions after you fill out a survey at the end. So I'll talk to you about that. Right. So integration by substitution. And some people really like this because it feels like a more formal technique for many. So this is where we can't use, or we're told a substitution to use, and we can manipulate what we're told as well. Because if they tell us u is x plus 1, of course we can also say x is equal to u minus 1. Now the aim of this is to make an easier integral. So we don't want to integrate it until we've got everything in terms of u and du as well. So we need to replace the x variable to start with, and we need to see how we go. So basically what we're going to have here, the integral we end up working out, is going to be between 2 and 0, and I'm going to keep them in purple as they're x bounds at the moment. And I'm actually going to replace x with u minus 1, and x plus 1 is u, so I'm going to replace that with u cubed. And unfortunately, I'm still in dx. This is where I'm at. The problem is we've still got a dx, and we've still got 2 and 0. Okay, so we need to change a few little bits still here. Okay, so we'll keep going. But hopefully that substitution so far is good. Now, to replace dx with du, what we need to know is since u equals x plus 1, we can work out du dx is equal to 1 and times up by dx. So du equals actually 1 dx. That seems a little bit easy or a little bit too nice, but sometimes that happens. So I actually can swap out dx for du. We also need to change the limits because they were x bounds. So remember, u is equal to x plus 1, and the x bounds we were given were were 2 and 0. So we're just going to add 1 to both of them. So 3 and 1. So basically my converted integral that I now have is I've changed the u bounds to 3 and 1. I have the integral of u to the 4 minus u to the 3. And I'm going to do it with respect to du because du is replaces dx. Okay, so the integral we're asked to carry out is basically that. And because we've changed the bounds, we can literally just do this. It should be a much easier integral than we started with. And if we give that a go and we sub it in, I think, I'm just going to check, 142 over 5 is what we get. Do check it. Okay, cool. So I'll leave that there for us to check. What I am going to do is I'm going to give you a practice one now to try and see how we get on. And then we'll do by parts before we take a break. So here's a practice question. Here's one we can do. And they give you a substitution. They give you this substitution. This is a really good one for you to try. I'm going to give you 3 minutes to look at this. 4 steps, du for the substitution. Trig identities might be helpful. Don't forget the constant. Here you go. 3 minutes. Give this one a go by substitution. The substitution is there for you as well. Another 2 minutes. We'll see how we go. Don't rush, but we'll go through this carefully. So it's quite a nasty one, but let's do our best with this. Okay, we'll go through this shortly together. It is quite a hard question, and there are a few little comments about this for different exam boards removing certain content. I know, for example, for Edexcel, people have said things like arcsign won't come up. If they give you a substitution like this, however, you will be expected to see it through. So I think this is a really important one to do together. Now, it almost feels like it's harsh for 4 marks, but let's have a little look. So first thing we can actually replace is x for sine squared u. So we can get that in terms of sine squared u. Check we're all happy with that. Now, this is really important because there's square roots, there's identities. 1 minus sine squared u you might recognize as something else. You can also do differentiation. There's lots of different ways we could start frantically approaching this. But straight away, I would immediately replace the x with sine squared u. So the substitution, we haven't always got to put u directly in. Sine squared u is fine. It might be a trig one where u is actually within another function. Now, where we go with this is we also need to sort out the dx bit. So if we differentiate sine squared u, we're going to get 2 sine u cos u. So if we all check we're happy with that. So 2 sine u cos u. Check we're good. And then I would probably times up by du so that I now have something that I can use to replace dx. I can replace it with all of that. Okay, so all of this can replace dx. Okay, now tidying this up further, this is what I have. Now, people get a little bit panicky, sometimes expanding it out and so on. But let's see where we go with this, because now we've got all the right letters. Now, some people will be like, okay, let's use the trig identity. 1 minus sine squared u is, of course, cos squared u. And people get a bit panicky because it's like a different trig function. But that's fine, because we've got a cos squared, we've got cos u on the top as well. And we're square rooting it. So this tidies up quite nicely. So we're going to end up with 2 sine u cos u over sine u cos u. So that's where we get to. So this is going to really, really simplify down to the integral of u 2 with respect to u. It's just putting it back at the end. We've got to be careful because obviously we want the answer back in x. Now, if you integrate 2 with respect to u, you're just going to get 2u plus c. Okay, so the integral is going to be 2u plus c. And of course, we have to put u back in. Now, remember, they didn't actually give us u. They gave us x is sine squared u. So if we rearrange this, we square root both sides and inverse sine it. That's actually what we've just found the integral as. 2 arc sine root x plus c. The answer looks horrible. The integration was really, it was integrating 2. Like, but it was the putting the substitution in that was dreadful. Okay, so I'm hoping that last bit makes sense, but that's why they gave you the substitution, because there's no way you could have just come up with that easily. So that was hopefully the last step is the bit we need to be clear on, and it became from because it was quite a hard substitution. So you square root and then you arc sine. Right, what we're going to do is we're going to look at integration by parts and then take a short break. So by parts is basically the kind of reverse process for product rule, okay? But what we actually have to do is out of the product of two things, treat one of them as the derivative of something and one of them as the integral of something. So if I give you an example here for this one, let me just check. We're good to go with this. Yeah. So this one here, we have to, and you might have different ways of denoting this. I'm going to do a more shorthand notation up here. Integral of u v dash is equal to uv minus the integral of vu dash. If you prefer it like that, is that okay? Some people prefer it sort of written kind of that way. Sorry, it's a bit crammed in the top. Now, what we're going to do is we're going to say what's u and what's du dx or u dash. And then we're going to say what's dv dx and what's v. Okay. Right. It does get more complicated than x and e to the 2x. But the first prompt, I would say, is the easiest thing to set up as the one we differentiate in this particular case is x, because when you differentiate it, it goes to 1. So it's going to make the problem easier. So well done. If you've got the little acronym for that, LIATE or whatever it is, tells you the order. This is pretty much what you're going to choose most of the time. It's only when there's a logarithm you have to look out for it. So u is going to be x, du dx is 1, dv dx is e to the 2x. So just be careful finding v, you have to actually integrate that. So integrating e to the 2x will be a half e to the 2x. So let's do this together. Now, if we sub it into this formula, then what we're going to get is x squared, oh no, sorry. This times this, oh no, losing the plot here. So x times a half e to the 2x minus the integral of the other way round, which will be 1 times a half e to the 2x with respect to x. Okay, so what we're going to do, we still leave ourselves with an integral to do, but it should be an easier one than the original question. And don't forget, guys, you can pull out the half out the front as here and just do the integral of that and then tidy it up. And what must we not forget? We mustn't forget at the end of it the plus c. So we are going to get, if we go through this together, x over 2 e to the 2x minus, then the integral of e to the 2x is another half e to the 2x. The half times the half is a quarter e to the 2x plus c. Well done if we got that. Hopefully that's all good. So key things, I've kind of written all over the positions here. They're the things we found. And then what we should have, I'll rewrite that final answer. Oops. Is we got x over 2 e to the 2x minus a quarter e to the 2x plus c. So let's give this a go. One quick practice and then we'll take a break. Here's your question for 5 marks to try by parts. My hint, for those that aren't aware, is we know how to differentiate ln as 1 over x. That will simplify the problem. That's probably how you want to set it up. You are also given a picture of the graph because we're using it to find an area. So it won't be a plus c, it'll be sub some values in. Right, I'm going to give you 2 minutes. We'll check some answers and then we'll take a short break. Here we go. Okay, so we're going to differentiate ln because we know how to do that. And it also will help simplify the problem because the derivative of ln is 1 over x, which will make things hopefully a bit nicer. Okay. So a suggestion here is u is ln x and du dx is 1 over x. That means that the v dash, the dv dx bit, is root x. So we actually then need to integrate that. That's the one tricky bit. So we need to add 1 to the power and divide by the new power. And that's what we're subbing in. Once we've got that, we plug it in simply to the by parts formula, which will be uv minus the integral of v du dx. And what we should find is the v du dx, the 1 over x cancels the x to the 3 over 2 in a nicer way. So this is what we get. We're going to get, and I've just skipped ahead to this part here. Don't worry about the bounds too much. 2/3 x to the 3 over 2 ln x minus the integral of 2/3 x to the 3 over 2 times 1 over x. That will tidy up to the integral of 2/3 x to the half. Now you can do that integration, and then sub the bounds in of e and 1. Okay, so I'll just give you a minute to have a little look at that. And if you sub those bounds in, leave it exact, our final answer is 2/9 e to the 3 over 2 plus 4 over 9. Now, I'll give you a minute to look over that. We're actually going to take a short break till just after 3 o'clock, I think we're going, and then we'll be doing our final session on statistics. Look forward to speaking to you then. If you've got any questions, keep them coming in. Really well done. You guys are doing so well today.